Hello there, welcome to this video. We're gonna do question number 6 on the energy, work and power examples, and this one will hopefully give you a sense of what kind of questions you can get asked in terms of efficiency, and it's also got some nice insights about solar panels and solar power. So let's get on with it. The question says the radiation received from the sun at the Earth's surface at the latitude of Great Britain is about 600 watts per meter squared, if there's no clouds. What area of solar panels would be needed to replace a power station of about 2 gigawatts if their efficiency is 20%? So the efficiency here refers to the efficiency of the solar panels. So first thing we need to do really is to convert the 2 gigawatts into standard form so that we make sure we don't make any mistakes. So what's 2 gigawatts? 2 gigawatts is 2 times 10 to the power of 9 watts. Okay, giga means to the power of 9, which is 1000 million, and megawatts would be to the power of 6, kilowatts would be to the power of 3, and so on and so on. So having written this down, then we can say, okay, so let's think about the area that it would take up. So my reasoning would probably go like this. I would say, well, if my pen is being a bit annoying. If the panels were 100% efficient, let's calculate the area, and then we can say, well, it's only 20% efficient, so then we can do the proportion later. So if the panels were 100% efficient, then the whole of these 2 times 10 to the 9 watts would be divided by all of the energy that's falling on each meter squared, right? On the whole 600. If every single watt was absorbed, then the amount of area would be, assuming that the whole 600 is taken by each meter squared of the solar panel. So all of this energy is what I'm trying to all of this power is what I'm trying to absorb, and this is the area, the amount of power that I'm absorbing with every meter squared. So this division should give me the number of meters squared that I need of solar panels, assuming that they're 100% efficient. So that comes out to be, to 3 significant figures, 1.67 times 10 to the 6 meters squared. So that's millions of meters squared. So that would be assuming that the panels were 100% efficient, but if 20% efficient, then let's see what's the relationship here. Since 20% of 20% is 20 over 100, which is 1/5 of 100%. Then we know that this is the number of sorry, I should have written here the units, meters squared. This is the number of units that meters squared that would be needed if the conversion was 100%. So here 20% is 1/5. So if they're telling us the panels are actually 20%, it means that this number here is 1/5 of the area that we're actually going to need, right? We're going to need a much bigger area because the efficiency is not 100, it's 1/5 of that. So we're going to have to take this as 1/5 of the real answer. So then if we want the real answer, we need to multiply that by 5. So if we take the full number without taking this one here that is rounded up, take the full number, then we need the whole fraction, 2 times 10 to the 9 over the 600. This would be assuming it's 100% efficient, but since it's not, it's only 1/5, we multiply by 5 and we can get the actual number of meters squared, which comes out to be 8.33 times 10 to the 6 meters squared. So that's quite a lot bigger than that, and that would be our answer for the first part of the question, which is how many meters squared would be necessary to substitute 2 gigawatts to substitute a normal power station that produces 2 gigawatts, and this is what it comes out to be. It's quite a big chunk of land. And in the second part of the question, they tell us that what percentage is this of the whole of the UK, and the UK, they tell us that it has a area of, so area UK is approximately 3 times 10 to the 11 meters squared. So what percentage is this here, substituting 2 gigawatt plant, what percentage is that of the whole area of the UK? So that's easy to do. The percentages, you normally write the smaller number on the top, choose yellow again, the smallest number on the top, and so the number that you're trying to compare with the full number, and the full number you write it at the bottom, and here you would get a fraction. So if this was half as big as that, you would get 1/2, but we don't want the fraction, we want the percentage, so then we would need to multiply that by 100. So if this was half of that, then we get 1/2 or 0.5, and then multiplying by 100 we get 50%. And in the general terms, just the smaller number divided by the bigger one multiplied by 100 comes out to be around 2.78 times 10 to the minus 3 percent. So that rewriting that, it would be, see, it's a 3, so I need 3 zeros, one of them before the dot and then another 2, and then the third number would be this one, and this one or the fourth number, third one after the dot would be this one. And since it's quite a small number, I'm only going to round out the first one and say 0.003% would be how much land is needed to as a proportion of the whole country to substitute a 2 gigawatt plant. Now we have a little bit more of a useful insight in the next part, where they say that in 1989 the total power station capacity in the UK is 120 gigawatts. And what percentage would have to be covered to substitute all the power stations in the UK? Well, that's easy, because if this is the percentage for 2 gigawatts, then 120 is 2 times 60. So if we just multiply this by 60, we would get the full percentage. So let's see. We are going to use the full number from the previous part instead of the rounded up number, and that works out to be, and I've just done this calculation again, and I've just realized that the power here is a 5, not a 3. And so this would have 2 more zeros here, and this needs to be corrected also. 0.00, that's 4 zeros in total, need a fifth one, 5, and then 3%. Okay, so it's a tiny area, percentage of the area, and with 120 gigabytes we just need to multiply this, as I just said, by 60, because we just did it for 2, we want it for 120, so times 60, then it would be that answer multiplied by 60, and we get a value of 1.67 times 10 to the minus 3 percent, which is about 0.002 percent, and this would of the total area of the Great Britain, of the total area of the UK. So that's not so much of a big area. Well, it's a big area, but the percentage is not very big. So the argument that this person is making is really that, well, the person who wrote the question, is that we could do you know, we could do, it wouldn't take so much of the UK to be able to provide it all with energy. But this is again assuming that there's no clouds, and that's not not normally the case in the UK. But if you did the same calculation for Spain, it would look much more favorable, because first of all, the amount of energy falling per meter squared would be bigger at that latitude. Also, there's just less clouds in general, so apart from there being more sunshine, there is less often cloud cover. And also finally, the area of the whole country is much bigger. Spain as a country is much bigger than the UK, so the percentage, when you work this out, would be a lot more favorable. It would be an even smaller percentage of the land than you would need in order to power the whole country. The question is whether the expense of setting all that up and building the solar panels is actually that environmental. When you look at it, it's a pretty cost-intensive, labor-intensive process, making solar panels, and you have to purify the silicon a lot. So they're looking for better and better materials all the time. And if the petrol starts running out soon, or the oil starts running out soon, then we're going to need to change from that energy onto another pretty quickly, and I'm not sure we have the infrastructure for that. But hopefully some other solutions will pop up also, and we'll be able to sort out this energy problem that we're starting to have quite heavily. Alright, so hopefully that gives you a little bit of an insight into solar panels, and also into what type of question you can get to work out efficiencies. And we'll look at the next question, number 7, probably in the next video, because we don't have that long left on this one. Until then, take care.